Raafat El-Hacha. I'm a professor at the University of Calgary, Department of Engineering, that's in Calgary, Alberta. And I'm the secretary of the IIFC, and it's my pleasure to present this webinar on the pre-stress FRP for the new construction. So if you have any question at any time, just please ask. Okay, so the objective of this webinar is to provide engineering students with guidelines that can be used in the design of members that are pre-stressed with carbon, aramid, and glass tendons. But what I'm presenting here is everything according to the Canadian code. We have Canadian code for the building, and there's also the bridge code. And in the bridge code, we have a section 16 that is devoted to FRP for strengthening and for new construction. So don't worry, if you're not familiar with the Canadian code, that's not a big deal. All the code, they are the same with very minor things. I would try to mention this. Again, I assume that you have a background in FRP. You know what's FRP, so I don't have this information. This is a general information. I skip it. I will go direct to the topic about the pre-stress with FRP. Okay. So the overview of this presentation or this webinar, that I will give a little bit of the history and the field application, followed by some design consideration, the property of FRP, tendons, anchorage, pre-stress losses, stress limitation according to the code, the flexural design, strength calculation, the limit state design, and a little bit about the ductility. Shear design, I don't go into much detail in the shear design, as well the bond development and unbonded pre-stressing. As you can see, it is a very heavy webinar, so usually it takes more than 1 hour. I'm gonna cover the things that I don't want to say the most important. Everything is important, but what at least give you the step toward design member with pre-stress with FRP. Okay, some historical development, demonstration project, field application. Again, I'm not gonna put many, so just gonna be few of those. But the historical development. Okay, so what happened here? Sorry about that. This is the. Okay, now I have this just to refresh your memory about the advantage of FRP. There's so many advantages, whether carbon, aramid, or glass. It's new structure that they give you longer life cycle. You will have a reduction in the maintenance cost of the structure, give you superior strength, and then the durability is way much better because of the property of the FRP that they have. They do not corrode. And the overall cost efficiency of the structure is going to be different or less, and you get new design options. It started in 1970, the research in Germany on GFRP for pre-stressing. Then it moved to Japan, as you can see in this very brief historical development. The USA in 1988. The Kepler was introduced in the United States in 1989, and the first GFRP pre-stress bridge was built in the USA in 1990. And then we have 2 applications in Germany in 1991. And then eventually they start to think about the design guideline. The first was in Japan, established in 1995, and then it's followed in many countries later on in Europe, in the United States, in Canada. This is the ISIS Canada. We have ISIS represent Intelligent Sensor for Innovative Structure. Now the name has changed to Simtrek. We do have Canadian code. As I mentioned, this is the only North American code. As I mentioned, Canadian Highway Bridge Design Code. First version was in 2006. The latest one, 2014. There's a chapter 16 devoted on the use of FRP in new construction and for strengthening. And then we have a complete code for building. This is the Canadian. American, they have the guideline. We have the ACI 440 Committee on Pre-stress FRP that we have a design guideline. The first application in Germany were the Marienfeld Bridge. It was the first bridge built in Germany with external unbonded GFRP pre-stressing tendon. Later on, we're going to see that some code, they have reservation about using GFRP and I will mention the reason about this. And then the Bass Bridge in Germany, 1991, where they used the carbon and the steel tendon as internal onboard and post-tension reinforcement. In Canada, first application was in 1998 in Province, Manitoba. They built the bridge to 2 lanes, 165 meters long. And it was one of the first bridges called the Taylor Bridge, as I mentioned. They have used a combination of different type of carbon from 2 different manufacturers, different texture of the bar. One of them is the CFCC, or the carbon fiber composite cable that looks like a strand, steel strand, twisted, and then there's the solid carbon reinforcement. So they combined using the 2 types. And then as well, in one of the girder, they used the stirrups made of the carbon, and another girder they used the epoxy coated. So you can see that one of the advantages of the FRP is the lightweight. So this is Professor Riscalla. He's holding the cage of the stirrups. This shows the fabrication installation of the fiber optic sensors. That's how they were shipped, and then they have used a steel coupler in order to perform the post-tensioning of the strand. Again, that's the photo of the hold up and then the hold down, and this is at the transfer zone. You can see the reinforcement in the girder. Construction, that shows the casting of the concrete facing the deck. And then they instrumented the bridge with fiber optic sensors. And if you go to this website, there is somewhere you can search on live monitoring, and you can get the map of Canada where you can select the application, and then you can click on it. It takes you to that to the website of the field application, and you can get more data. And this is, for example, if you go to that website for live data, you select, for example, Taylor Bridge. We have a camera where you can maneuver the camera from your office, and it give you the video, live video, and then here the data of the strain versus time. The other application is in Calgary in Alberta, the Beddington Trail Bridge, and it was the first time that they used the bulk T bridge girder pre-tension with carbon tendon. The shear reinforcement was made of carbon, and they have monitored with the fiber brag sensor. Another bridge in the United States that was opened in 2001. This is the interesting bridge where they use bonded and unbonded carbon in both longitudinal and transfer directions. And this shows that there are 2 bridges side by side, structure A, structure B. In one of the structures, they use conventional H2 I-beam reinforced internal with pre-stressed steel. The other structure B, they use the beams were pre-stressed with the carbon in longitudinal and transfer direction. That's a bottom view showing the longitudinal carbon cable, post-tension strand, the saddle point, and this in the transfer direction. They use a different type of carbon. So that's very brief about the historical development and the field application. Then I move on to the general consideration related to pre-stress. Again, I assume that you have some background on pre-stressing, but I do have a few slides that gives you general consideration about something that you need to think about when you do design with the pre-stress. Again, pre-stress, this is taken from the code. Concrete, pre-stress concrete is a concrete when you introduce some stresses, in addition to the stress resulting from the dead and the other load that are counteracted to a desired degree. So you're the designer, you have the freedom in your design. And then there are 2 different methods, the post-tension and the pre-tension, where the method of pre-stressing, the tendon are tensioned after the concrete has hardened. The pre-tension is the method where the tendon are tensioned before the concrete is placed. The forces, if you look at this figure here right now, at any section along the length of the member, there are the internal forces due to pre-stressing forces. These are the components. So if you have this parabolic or whatever shaped braid profile, You have the pre-stress force. There are two components, the axial and the vertical component as well. There is a bending moment that is due to the eccentricity of the pre-stress force. Okay, now when you do pre-tension member, so the magnitude of the pre-stress force is constant along the length of the tendon. However, this is not true for a post-tension because of the friction that happens between the tendon and the duct. So there are some time-dependent pre-stress losses. And because of this, the pre-stress force will be reduced over time. And when you do the flexural analysis and design, you have to know two values for the forces. We have the initial pre-stress force, which is after the transfer of the pre-stressing force. This is not the jacking. We have the jacking. This is the amount of pre-stress you put in the cable. And there's the initial pre-stress after transfer. And then we have the final or the effective pre-stress after all the losses have occurred. So we're going to talk about how you determine these forces and what are the losses that you have to account for when you do the design. Now, also under the general consideration that there are two cases that must be considered during the analysis and design under specified load. As you know, in the pre-stressed member, you design for service, you check the ultimate strength. However, in design of reinforced concrete, you do the design for ultimate and you check the serviceability. So it's vice versa. So that's why you need to know what's the initial pre-stress force. It is the maximum force that you combine it with the minimum unfactored service moment, okay, which is the load causing the minimum moment is normally the self-weight of the girder. The other case is that where you have the final or the effective pre-stress force, and this is the minimum force combined with the maximum moment due to specified load. So by combining the stresses from the pre-stress force, there's eccentricity and the moment at different stages, you determine the stresses, and these stresses in the concrete must be less than the maximum limit imposed by the code. If you satisfy this, then everything is okay. You move and you check the ultimate strength. So the top and bottom concrete fiber stresses resulting from these two cases, they must not exceed certain limit imposed by the code. Okay, now we're going to move to the design of for flexure. What are the restrictions, serviceability, and here I have another one is related to a comparison between the strengths of steel versus the strength comparison between steel and FRP pre-stress member. Okay, remember I mentioned about the different stages. So these are, we have the first one is that at the pre-stress transfer. This is what we call the newborn, and then we have the young stage, which is the structure under the service load, the long-term service, this is middle age, and the ultimate, this is where you have to make sure that under extreme event that this structure is able to survive. Now, we consider in the pre-stress, we consider the member as uncracked in all except that for ultimate, definitely, we know why. And then I mentioned about the time-dependent changes in the material property that you have to look at the concrete gain strength and stiffness over time. You have to look at the creep and shrinkage in the concrete. They cause the stress reduction. And what's important actually is the relaxation in the pre-stress reinforcement. Although all of this will cause reduction in the stress. Now, earlier I mentioned that some code, they have restriction on the use of GFRP when it is highly stressed, because there's a potential that the GFRP pre-stress tendon will deteriorate, especially if it's in an alkaline environment when it is in direct contact with the concrete or cement base. So the Canadian bridge code, they permit you to use GFRP as internally bonded pre-stressing reinforcement. However, the Canadian building code does not allow you to use the GFRP as internal bonded reinforcement. Okay. When it comes to serviceability, we know that the modal plasticity of the fiber reinforced polymer, especially aramid and carbon, they are about 1/4 to 2/3 of the steel. So deflection of pre-stressed concrete beam using FRP tendon, it's going to be larger than that of a similar concrete beam pre-stressed with steel tendon. Now, The relaxation losses in FRP also reduce deformation due to time-dependent effect. So the method of computing this tendon stresses must specifically account for these conditions. Okay, that the most important, one of the important things is that this deflection is going to be larger because of the monotonicity is smaller. Okay, so if we look at a comparison of the strengths, so when you have pre-stressed steel tendon, the designer assumed that that as a result of the significant deformation occurring after healing, that you have sufficient strain capacity in the steel reinforcement to develop the compressive strengths remaining after the pre-stressing, after pre-stress. So designed for failure by concrete crushing. However, this assumption is not valid. Oh, sorry. This assumption is not valid for FRP. Because FRP has a linear stress-strain relationship until failure. Okay. So what happened here that when you do the design or the analysis, you have to do what's called the budgeting, the strain capacity of the tendon between the flexural and the pre-stressing requirement. So what's required for to give you the flexural ultimate strength and the requirement to do the pre-stressing. Because of you doing this budgeting, so this balance may require you that you have to lower the initial pre-stress in the FRP in order to achieve sufficient deformation at ultimate. So you need that to be higher. So meaning that you have to lower the initial pre-stress. So sometimes this is this can be misleading, you know. So steel tendon, they are typically stressed to about 80-85% of their ultimate strength during jacking, or which about 0.5 to 0.7% strain. However, the allowable stress in the FRP tendon tend to be lower because the stress rupture limitation we talked a little bit about earlier, and then they fail into pre-stress range of 40 to 60%. So for steel, we jack to 85%. However, for FRP, we jack to less. So this doesn't mean that you have less strength in the FRP because you're jacking to force lower, you know. So that's what I mentioned, that this lower range of allowable stress might be misleading. However, it represents a corresponding strain about 0.7 and 1%, which what we have for steel. So it's around 1 to 1.4 times the typical pre-stressing strain of steel. Okay, so we shouldn't be confused about this lower pre-stress range, that 40 to 60%. That this is something that is not good, you know. So now many researchers have assumed that since large deflection can be achieved in member pre-stress with FRP tendon, the ductility requirement, we can talk about this later on, the ductility requirement can be satisfied. So this is a very dangerous assumption, since large deflection may be due to the low modulus of elasticity of the reinforcement, okay, and may correspond to large amount